Hello students, welcome back. So we were in the discussion of a very important chapter of electrochemistry. So today we are going to talk about concentration cell and we are going to solve some problem related to concentration cell and all the topics that we have covered till now. So in the previous lecture we were discussing about different type of half cells. Okay, so we talked about 4 different kind of half cells. First was gas ion electrode. Okay, we derived the Nernst equation for them as well. Then followed was metal ion electrode, then metal insoluble salt common ion electrode, and the last which we did was a redox electrode. There are 2 or 3 more kinds of electrodes, half cells, which we will cover as we proceed further. For the time being we will stick to these 4, and I hope you have done your homework well and you have studied all the parameters that I have taught till now, because all of the questions will be based on that only. Okay, so let's start the lecture. So the first thing that I wanted to discuss today was how do we find pH using a hydrogen electrode. Okay, so you can see in the figure, this is basically a standard hydrogen electrode. What we are doing, okay, there is a platinum wire dipped in the aqueous solution containing H plus ion, and to this solution we are bubbling hydrogen gas. So hydrogen gas is bubbled inside the solution. The hydrogen gas is at 1 bar and the H plus ion is having a unit concentration. So this is basically a representation of standard hydrogen electrode. Okay. Now we have already told that standard hydrogen electrode has a reduction potential of 0. Okay. So this point is very important. I hope you could easily make it out now. So we told that the reduction potential of hydrogen ion cell is always 0. Okay. Now suppose if we take some different concentration. Okay. Suppose instead of 1 molar we are taking any concentration, say 10 raised to minus 3 molar. So then that would not be a standard hydrogen electrode. Okay, standard here refers that the temperature has to be 298 Kelvin, pressure of the hydrogen gas has to be 1 bar and the concentration of the H plus ion in the solution has to be 1 molar. If you change the concentration, then obviously it will not remain a standard electrode. Okay, so suppose we are having a cell. Okay, suppose we are having a half cell. Okay, which we are representing something like this. Say we are having H plus ion. Okay, its concentration is say C1. Okay, its concentration is not 1 molar now. Okay, so this is changing into hydrogen gas. Okay, whose pressure has been given to us say as 1 atm. Okay, and then there is a platinum electrode. So you can see that this is a representation of a half cell of gas ion electrode or hydrogen ion electrode. Okay, now you can see that the way it is written, it easily communicates that it is a cathodic half. Okay, because H plus is gaining electron and changing into hydrogen gas. Okay, so let us write the equation first. Okay, so we will say that this terminal would behave as a cathode because reduction would take place in this segment because it is written in that manner itself. Okay, so H plus will take up an electron. So H plus aqueous will take up an electron. Okay, so 2 H plus will take up 2 electron. 1 H plus on taking up 1 electron will change into atomic hydrogen. 2 H plus on taking up 2 electron will change into 2 atomic hydrogen, which will combine and form a hydrogen gas. Okay, so we know that its standard reduction potential is always 0. Okay, so we can write it standard reduction potential. Okay, so if we want to write the EMF of this cell using the Nernst equation, so we will say that EMF, which is H plus changing into hydrogen, will be equal to E naught of this electrode. Okay, we are just basically applying the Nernst equation, minus 0.0591 upon 2 because n over here is 2. Okay, n is the number of electron exchange between the different electrode, or in this case because it is only a half electrode, so n is basically the number of electron transferred, number of electron gained or lost. Okay, so I can write this as log of partial pressure of hydrogen divided by concentration of H plus raised to power 2. Okay, I hope this is clear to you. So this is the Nernst equation. So we know that E naught of this cell is 0. Okay, so this is 0 minus 0.059 upon 2 log of Pressure, we also know the pressure of hydrogen is given as 1 atm. So this would be log of 1 upon H plus raised to power 2. Okay, so we'll take this above. So this will become E H plus changing into hydrogen would be equal to minus 0.059 upon 2 log of H plus raised to power minus 2. Okay, so we'll use the basic rule of logarithms. Okay, so this minus 2 will come outside. So this will become minus 0.059 upon 2 into minus 2 into log of H plus. Okay, so this 2 and 2 will cancel. So this will become E of this half cell is equal to 0.059 into log of H plus. Now we know that pH is minus log of H plus. Okay, so this is what we know. pH is minus log of base 10 H plus. So we can write log of H plus as minus of pH. Okay, so I can just write instead of log of H, I can write this as minus pH. Okay, so this becomes the expression. So if you want to write, so this will become E equals to minus 0.059 into pH. Okay. Now one thing which you have to remember, the most common mistake that student makes over here is they simply memorize the formula and try to solve the question. Okay, first you have to look what has been given to you. You can clearly see that this is a cathodic electrode. Okay, so this is acting as a cathode, so it will gain electron and change into hydrogen. So you are writing in terms of its reduction potential. Okay, so you can see that we are writing in terms of reduction potential. We could have also expressed in terms of oxidation potential, then the expression would have changed. Okay, so this is the expression. So question can come, find the EMF of this cell. Say the concentration was, okay, if the concentration is 1 molar, you can see that if C1 is 1 molar, if you take pH, pH is minus log of H plus, so log of 1 would be 0, so E would become 0. Okay, if you take say any other concentration except 1, so say the C1 was given as 10 raised to minus 2, so you have to just take the pH, so that would be 2, so you have to just multiply the EMF, just multiply the minus 0.059 into pH, you will get the EMF of the half cell. Okay, hope this is clear to you. So this is a very important expression. Okay, if in the question it is written that, suppose a question says that find the pH of a hydrogen electrode whose EMF is say 0.118, okay, so minus 0.118, okay, find the pH of a hydrogen electrode whose EMF is minus 0.118. So nothing has been written, it has been written that the EMF is minus 0.118. So by default EMF is means that it is the reduction EMF or the reduction potential. Okay, so you have to take that whenever there is anything written like the standard reduction potential is not written and reduction, and only it is written that the potential of the cell is minus 0.118, then you have to assume it as a reduction potential. So by default, if it has not been mentioned to you about oxidation or reduction, so you have to always take it as the reduction potential. Okay, so reduction potential will be given to you, you can find the pH. Okay, hope this is clear to you. You can take a snapshot of this. Okay, now let us just consider another case. Okay, now suppose this terminal is acting as a cathode, so we can write this as something like this. Okay, so this is acting as a anode. Okay, so we can write this, okay, something like this. So this is acting as an anode. I have already told you while doing the sign convention in the previous lecture, okay, representation of cell. So if it is acting as an anode, you have to enter into the anode, you will enter it through the rod. So you will encounter platinum first, then you will encounter the hydrogen gas that is going inside the solution, and then you will get the H plus ion. Okay, so in this case, if it is acting as an anode, so we know that it will get oxidized. Okay, so it will get oxidized. Okay, you have to just like be very skillful in applying the Nernst equation. We can apply the Nernst equation on the half reactions or the half electrode, but you have to see that you are using the right concept. Okay, now because this is the oxidation reaction, so suppose I write the oxidation potential of this as we know that the oxidation potential of this is 0 only. Okay, so the EMF or the oxidation potential of this electrode would be E naught H2 H plus minus 0.059 upon 2, because again the number of electron change is 2, into log of H plus concentration whole square divided by partial pressure of hydrogen. Okay, now again the partial pressure of hydrogen, say we have taken as 1 atm. If it is not 1 atm, then we have to find accordingly. Okay, so I hope that is easily understood now. So we know that the oxidation potential of this is also 0. Okay, so this will become minus 0.059. We'll take this 2 inside. So this will become log of H plus. Okay, so I can write this as E of H2H plus is equal to minus 0.059 into log of H plus. Now we know that pH is minus log base 10 H plus. So I will take this negative along this log of H plus. So we'll get oxidation potential as, okay, we'll get the oxidation potential as 0.059 into pH. Okay, so again, if pH is given to you, we can find the oxidation potential at any other condition using this formula. Okay, so you have to understand how we are writing the Nernst equation. If you are very clear in the basics, if you are able to write the oxidation and reduction half cells and you are able to write their Nernst equation, then things become very easy. Okay, so again I have already told you, it starts right from the scratch. You need to go to the very basic level and then keep on enhancing yourself to solve the high level problems. Okay, so once you are clear with all the basic elements that students often make mistake, then going to the higher level problem solving is a very easy task. Okay, so I hope this is clear to everyone. So this is how we find the pH using a hydrogen ion half cell. Okay, hope this is clear to you. Okay, the fifth kind of electrode is a Kuhn hydrogen electrode. Okay, now generally Kuhn hydrogen electrode is not asked in the JEE, but we'll have the basic understanding of what is Kuhn hydrogen electrode. So basically what happens in this, a platinum wire is dipped in a solution containing a Kuhn hydrogen. Okay, so basically Kuhn hydrogen is like the reaction that is happening in the Kuhn hydrogen electrode is this. So this is basically a quinone. Okay, so this is basically a quinone, also known as benzoquinone. It takes up 2 H plus and 2 electron and changes into quinol. Okay, that's why we are saying it as Kuhn hydrogen. Okay, so this is basically quinol. So this is Kuhn hydrogen quinol. So platinum wire is dipped in the solution containing Kuhn hydrogen and quinol. So I can write this as Q. Okay, it is taking up 2 H plus and taking up 2 electron and changing into QH2. Okay, the reduction potential value has given to us as 0.699 volt. Okay, so this is the reaction that is happening in a Kuhn hydrogen electrode. Okay, so we can write the Nernst equation for this as well. So we know that E of QH2 would be its reduction potential, standard reduction potential, okay, minus 0.059 upon again number of electron that Kuhn hydrogen is or the quinone is gaining is 2. So N is 2 into log of concentration of QH2 divided by concentration of Q into concentration of H plus raised to power 2. Okay, again we can find the pH or the H plus concentration in the solution knowing the EMF, okay, of this half cell, okay, and the concentration of QH2 and Q. So from that we can calculate the concentration of H plus. From there we can calculate the pH of the solution. So this is the fifth type of electrode, which is Kuhn hydrogen electrode. Okay, a platinum wire is dipped in a solution containing quinone and quinol, where quinone undergoes reduction, takes up 2 electron in acidic medium and changes into an aromatic quinol. Okay, so we know the reduction potential value, so we can write the Nernst equation for this as well. So on writing the Nernst equation we will get this. Okay, so we will get the concentration of this. So if suppose they are similar, so they will get cancelled out. Okay, so E would become E naught minus 0.059 log of H plus raised to minus 2. Okay, you can take this minus 2 outside, so it will become E equals to E naught plus 0.059 into log of H plus. So basically the expression will become E will be equal to E naught minus 0.059 into pH. So we'll know the value of E, we know the value of E naught, we can calculate the pH of this particular solution at which this reduction reaction is happening. Okay, hope this is clear to you. Okay, so let us do some problem solving on what we have done in the previous lecture. So just read this question. This question says that what is the SRP? SRP is basically standard reduction potential for this electrode. Okay, sulfide ion, copper sulfide and copper half cell. Some data has been given to you, given solubility period of copper sulfide is given to you as 10 raised to minus 35 and the reduction potential of copper 2 plus changing into copper is given as 0.34 volt. So we need to find the reduction potential, standard reduction potential of this half cell. Okay. Now I have already told you, like when we are starting this program, that ionic equilibrium will find a lot of application in 12th class portion, especially in electrochemistry, especially in solutions and even in solid state. And like also we did some questions on chemical kinetics also that had some basic idea of ionic equilibrium. So again, I have already repeated time and over again that ionic equilibrium is one of the most important chapter which you should be knowing. Okay, even if you find it difficult, try to remember the basic formulas that are used, because in such kind of question only basic formulas are required and no high level detailed conceptual approach is required. Okay, but if you are having a very good hand in ionic equilibrium, you have done a very good amount of solving and you have taken that topic to a very good level, then definitely things become very easy. So I would recommend you, if you have not yet seen the ionic equilibrium lectures, I have already when this program started, I have already taken the ionic equilibrium lecture. So that is basically a 6th lecture. So that will revise you all the basic concept of ionic equilibrium. Okay, so this question has some application of ionic equilibrium. Okay, so let us solve this question now. Now the first thing that you have to do, like you have to understand the algorithm of solving. Okay, it's not that you read a question and you start doing anything. Okay, you need to have a very set algorithm. Upon that you will be solving. Okay, so all the questions that will come, you should have an approach, you should have a basic algorithm of how to approach the question. Then only you have to practice it again and again and the questions will become very easy. That is the most important strategy that you should use over here. Okay, so just first look at the reaction that has been given to us. Now we can see that there is a copper. Okay, so this is a metal, copper sulfide, it's metal, salt. Okay, copper sulfide, we know that sulfides are generally precipitates. Okay, sulfides of generally transition elements are precipitate. So this is copper sulfide, so this is metal, copper is the metal and its insoluble salt, that is copper sulfide, and a common ion is given to you. That means this is basically a metal insoluble salt common ion electrode. So this is the common ion insoluble salt and this is the metal. So we need to find the reduction potential of this particular cell. Okay, so we'll write this reaction. Okay, so its reaction would be copper sulfate solid is taking up 2 electron, changing into copper solid plus sulfide ion. Okay, this is the reaction that is going. Copper sulfide is changing into, that is copper 2 plus is changing into sulfide ion. Okay, so copper sulfide as a whole is taking up 2 electron, copper 2 plus is changing into copper and sulfide ion is coming out. Okay, so I hope you can easily make out that this is a metal insoluble common ion electrode. Now in the previous lecture I have done a very important derivation of relationship between a metal ion and a metal insoluble common ion electrode. Okay, I hope you remember that formula. So I have already told you that E naught of a reduction potential of a metal ion, okay, common ion electrode is always equal to the reduction potential of metal ion metal plus 0.059, okay, plus 0.059 upon n here is 2 into log of base 10 Ksp. Okay, I hope you remember this formula. In case you have forgotten this, just go to the previous lecture and you can see this how we have derived. So first we will write the Gibbs free energy of this electrode. Okay, then we'll write for copper 2 plus 2 electrons changing into copper. So we'll get the Gibbs free energy of that particular also. We'll rearrange them. Okay, and we'll get the final equation as copper sulfide solid changing into copper 2 plus sulfide ion. So we'll get delta G for that also. We'll compare and we'll get this expression. Okay, I hope you remember this formula. Okay, so a relationship between a metal insoluble salt common ion electrode with metal ion electrode is always this. Okay, so reduction potential of that metal insoluble salt common ion is always equal to the reduction potential of metal of that particular metal ion electrode plus 0.059 upon n is the number of electron, okay, into log of Ksp. So you can directly use this now. So E naught we know is 0.34 plus 0.059 upon 2 into log of 10 raised to power minus 35. Okay, so this will come out. So this will become 0.34 minus 0.059 upon 2 into 35. Okay, so when you do the calculation, I think the answer should come as minus 0.69 something. Okay, so C is the correct answer. Okay, so if you look at this question, this is a very standard question for JEE Advanced. Okay, so only thing that you need to know is the relationship between them. Okay, now you have to understand how it is coming. If you are just memorizing the formula, chances are that you will get lost in the examination and you will forget and you will mess up with this question. But if you are clear with the approach, with the steps, then this becomes very easy. Okay, so we have derived this in the previous lecture also. I hope you remember this formula now. Okay, so let us look at the second question. Okay, now this says that we have been given two reduction potential data. Okay, one that of PbBr2 taking up 2 electrons changing into Pb plus 2 Br negative, and second of that of lead. Okay, so its E naught is also given to you. Okay, so again you can see that there are two ways of approaching it. We can directly use the formula also. So you can see that this is the lead 2 plus and Pb. Okay, so this is the reduction potential data of Pb2 plus changing into Pb is given to you. This is minus 0.126 volt. Okay, now if you look at this PbR2, because it is written as solid, that means it is a sparingly soluble salt. So it is taking up 2 electrons changing into lead and we are getting an anion. So this is basically a metal insoluble salt common ion electrode. Okay, so I can write the reduction potential of this as this is given as minus 0.248 volt. Okay, so I know the relationship between them. So E naught, okay, of metal insoluble common ion electrode is equal to the reduction potential of, okay, metal ion metal electrode plus 0.059 upon n. Obviously you can see that number of electron transfer or the number of electron involved is 2 into log of base 10 Ksp of PbBr2. Okay, so you can calculate this. So we know the value of this, which is minus 0.248. We know the value of this, which is minus 0.26 plus 0.059 upon 2 log base 10 Ksp. Okay, so you can just take this over here. Okay, and this becomes very easy now. So this is basically minus 0.122. Okay, into 2 divided by 0.059. This is equal to log of Ksp. Okay, so just calculate the Ksp. So Ksp would become 10 raised to a minus. Okay, so this will become 10 raised to a minus 0.122 into 2 divided by 0.059. Okay, so I think when you calculate this, this will come out to be, so A is the answer. Okay, so look at the question. It's a, I will not say that it is simply a formula based question. It is a very good level question. Okay, it is definitely a question that can be asked in JEE Advanced, but because I have undergone these cases in my theory, so my understanding has become strong. I can directly use my basis of theory and solve these questions. Okay, and now suppose if you don't know this formula and if you don't know the theory about this, so how we are going to solve this now? So let us look at the real approach, okay, through which we have derived this formula as well. So we will say that we need to find the solubility product of PbR2. So first we will be dissolving PbR2 in water and forming a saturated solution. So once it has formed a saturated solution, it will dissociate into some Pb2 plus and 2Br negative. Okay, so we need to find the Ksp. So we know that the value of Ksp would be concentration of Pb2 plus into concentration of Br negative raised to power 2 when the solution has reached saturation, okay, or the equilibrium has been established. So we need to find the value of this. Okay, so we have been given this two equation. Okay, so we need to derive this equation first. Okay, so we need to derive this equation using the two equations. So clearly we have to just reverse the first reaction. So when we reverse the first reaction, we'll get we have to reverse the second reaction, okay, because if you can see that in this reaction PbBr2 is there in the reactant. So in the first reaction PbR2 is also in the reactant. So we need to reverse the second reaction so that Pb2 plus comes in the product, because Pb2 plus in the second reaction is in the reactant. So we are going to write the first equation as it is. Okay, so this is forming Pb solid plus 2Br negative. Okay, so we know the EMF as minus 0.248. Okay, so I will write the reduction potential as minus 0.248. Okay, now we'll reverse the second reaction. So when I reverse the second reaction, so this will change into this. Okay, so the oxidation, because it is undergoing oxidation, so I will write it oxidation potential. I can also write the reduction potential, there is no harm. Okay, so I have already told you in the first class that the overall EMF is always reduction potential of cathode minus reduction potential of anode. Okay, but we can also use reduction potential of cathode plus oxidation potential of anode. Okay, so both are the same thing only. So just add these two reactions. So when we add, the electrons get cancelled out, the lead get cancelled out. So we get PbBr2 changing into Pb2 plus aqueous plus 2Br negative. Okay, so the E0 cell of this reaction is minus 0.122 volt. Okay, hope this is clear to you. Okay, now we'll write the E cell. So E cell is equal to E0 cell, which is minus 0.122 minus 0.059 upon 2 into log of concentration of Pb2 plus. Okay, I will write it over here. I think it's not visible to you. Okay, so I will write E cell as E0 cell, which is minus 0.122 minus 0.059 upon 2 log of Pb2 plus into Br negative whole square. Okay, PbR2 is solid, so we don't have to write in the reaction quotient expression. Okay, so you can see that if this attains equilibrium, then only we will be able to find out the solubility product. So if this attains equilibrium, we know that at equilibrium E cell is also 0. So this will become 0. So this is minus 0.122 minus 0.059 upon 2. Now this will become Ksp, because Ksp is Pb2 plus into concentration of Br negative whole square. So from this you can also calculate, the answer will come as A only. So that, like, this was what we were doing using that formula also. So this is how we are approaching it. So what we are doing in this case is, we are taking this as a cathode and this as a anode, and we are combining them. So this we have taken as a cathode and this we have taken as a anode. So what we have done, we have taken a anode of Pb dipped in a Pb2 plus solution, okay, and we have taken this as the cathode. So what is it exactly? This is Pb, and we know that some amount of PbR2 is present. and so the lead is dipped in a solution containing Br negative, okay, and a paste of PbR2 is applied at the metal. So this is how you construct metal insoluble salt, common ion electrode, and this we have joined through a conducting wire and a salt bridge is attached to them. Okay, so this is the overall cell, the EMF of which is that. Okay, now if this cell attains equilibrium, then we know that E cell will be equal to 0, and from there we can calculate the value of the KSP. Okay, so I hope this approach is also clear to you. So we can either use the two concepts, but personally I generally favor the formula because I have done the basics first. I have understood how we are going to apply those formula in the direct questions. Okay, so hope this is clear to you. Okay, so again this is a very important question that can be asked in JEE Advanced. Okay. Okay, so next approach that comes is Latimer diagram. Now Latimer diagram, and there is one more diagram called as Frost diagram. Now these are very important diagrams that help us to predict the different oxidation state at different electrode potential. Okay, so Latimer diagram basically tells us about the relationship between the electrode potential and the different oxidation state of the metal. Okay, so let us first look at its definition. So Latimer diagram is basically the oldest and the most compact way to represent electrochemical equilibria for substances that have multiple oxidation state. Okay, electrochemical potential values are written for successive redox reaction from highest to lowest oxidation state, typically under standard conditions in either strong acid or in a strong base. So basically Latimer diagram is the representation of different redox reaction with respect to its standard reduction potential. Okay, so let me take an example to make you understand this. Suppose we are taking this as a reaction. So O2 is changing into H2O2. So O2 is undergoing a change in its oxidation state. Okay, so O2 is changing into H2O2 and H2O2 is changing into H2O. So when O2 changes into H2O2, okay, we can say that its standard reduction potential is plus 0.68, and when H2O2 changes into H2O, we will say that its standard reduction potential is plus 1.78, and when O2 directly changes into H2O, its standard reduction is plus 1.23 volt. So this diagram is basically your Latimer diagram. So you can see that the different redox reaction that is happening, okay, with the change in their oxidation state are represented, okay, along with its standard reduction potential. So that is basically your Latimer diagram. So in a Latimer diagram, what we do is we write different species, okay, and they are getting converted into different species through a reduction or a oxidation reaction, okay, and we write its EMF. So the diagram which is having the different oxidation state of a metal along with its reduction potential is generally termed as a Latimer diagram. So let us take an example to understand. Okay, suppose again this is a Latimer diagram. So what is it is showing that copper 2 plus is getting reduced into copper plus. Okay, so copper 2 plus is getting reduced into copper plus. So its standard reduction potential is X volt. Now when copper plus gets reduced into copper, its standard reduction potential is Y volt. Okay, now copper 2 plus can directly change into copper, so its reduction potential is Z volt. Okay, so you can see that the different oxidation state of copper or any metal which shows different variable oxidation state are connected with their standard electrode potential. So the diagram representing it is called as a Latimer diagram. Okay, now suppose we want to find out the relationship between X, Y and Z. So how do we find the relationship between X, Y and Z? So for this what we will do, we will first write the different equations and their standard reduction potential. Okay, so let us take the first reaction. In the first reaction we can see that copper 2 plus is taking up one electron and changing into copper plus. Okay, so copper 2 plus is taking up an electron and changing into copper plus. Now we know that its standard reduction potential is, okay, so its standard reduction potential is X volt. Okay, now let us look at this. Copper plus is taking up an electron. Okay, copper 2 plus is taking up an electron and changing into copper. Okay, the reduction potential of this is given by Y volt. Okay, now you can see that copper 2 plus when takes up 2 electron and directly changes into copper, its standard electrode potential is given by Z volt. Okay, hope this is clear to you now. Okay, now we need to find the relationship between x, y and z. Okay, now one thing that you can see, if we add first and second equation, okay, if we directly add the first and the second equation, you can see that we will get the third equation. Okay, so you just add this, copper plus will get cancelled out, copper 2 plus 2 electron will change into copper solid. So can we write that Z equals to x plus y, because we have added two reactions, so we should add their EMF as well? This is incorrect, because EMF is a intensive function. Okay, I hope you remember this. We have done this in thermodynamics. Okay, so EMF is basically an intensive function and is not additive in nature. Okay, so intensive functions are those which are not additive. Okay, so EMF is an intensive function. So we cannot directly add the two equation and get another half cell reaction and say that the EMF would be the sum of the two EMF. Okay, so you need to differentiate the idea of a full cell and a half cell. Now in a full cell, what we were saying, we were taking reduction potential of cathode and the oxidation potential of anode, and we are adding them to get the overall EMF. Okay, but in the final reaction, okay, in the final reaction of the overall cell, there was no electron present. But when you add these two reactions, in the final reaction, you can see that there are electrons over here. Okay, so this means that this is not the full cell. This is again a half cell. So what we are doing, we are taking one half cell, we are taking other half cell, and we are deriving the EMF of a third half cell. So for such cases, we will not say that you can add EMF, because EMF is a intensive function. So what we are going to do here, we are going to take the help of an extensive function which is a Gibbs free energy. Okay, so we know that, let the Gibbs free energy of this is delta G 1. Okay, so we know that delta G is minus, delta G naught is minus n into E naught into F. Okay, so n over here is 1 electron is taken up by the copper 2 plus, so this is 1, and EMF we know is x into F. Faraday is the charge on 1 mole of electron. Now let us calculate the Gibbs free energy for this reaction. So we write the Gibbs free energy change as delta G2 naught. Okay, so this will be again minus n into E naught into F. Now n over here is 1, E naught over here is reduction potential is y, so this is minus y into F. Okay, now let us look at the change in Gibbs free energy of the third reaction, delta G naught 3. Now the n for this is 2, so this would be minus 2, reduction potential is Z into V, into F. Okay, so this is minus 2 into Z into F. Okay, now when we are adding two reactions, we know that from Hess law of constant heat summation that the new reaction that is obtained will have the energy equal to the sum of all the reactions that have been added to give that particular reaction. So we know that when we have added these two reactions, so delta G naught 3 should be equal to delta G naught 1 plus delta G naught 2. Again, energy is a extensive function. So delta G naught 3 we know is minus 2 into Z into F. Okay, delta G1 naught we know it is minus x into F. Delta G2 we know it is minus y into F. Okay, so F will get cancelled out, minus sign you can cancel out, so Z will become x plus y. Okay, x plus y by 2. Okay, we'll just erase this. Okay, so hope this is clear to you. So this is again a very important question that can be asked in mains as well. Okay, so you will be given say reduction potential of this, you need to find the reduction potential of this. Okay, so you have to remember you are finding a reduction potential of a half cell. Okay, so you have to use the extensive function, that is change in Gibbs free energy. Okay, now question can come something like this also. Say you have been given a oxidation potential of copper plus changing into copper 2 plus. Okay, oxidation potential is given, reduction is not given. Copper plus is changing into copper 2 plus, say oxidation potential was given as x. Okay, so its reduction potential would become minus x. So when you are writing this expression of delta G, this would be minus n, which is 1, into E naught. E naught is now minus x into F. So it will become x plus x into F. Okay, so you have to take care of the data that has been given to you. So I have already said this time and over again. I am like always going to say this. You have to be very, like, you have to scrutinize the data properly. Okay, the main problem in JEE is questions are very elementary, very basic, but there is a slight modification or change in the data, or something has been given to you that may miss your eye. So your observation should be very strong in such cases. Okay, you need to understand the data that has been given to you, and that comes only through the approach of subjective questions. When you solve a lot of subjective questions, you get that habit of reading the questions, and that actually helps you in enhancing your skills. Okay, so this is how you do it. So Latimer diagram is basically a representation of different oxidation state of metal with its standard reduction potential. Okay, so I hope this is clear to you. You can take a snapshot of this as well. Okay, hope this is clear to everyone. So let us talk about the topic that we wanted to discuss today, that is concentration cell. Okay, now concentration cells are basically those cells which are made by combining two similar cells. Okay, so we combine two same cells and form a complete new cell. Okay, so I have already approached this concept that we need to have an anodic half. Okay, say like this is the anodic half because this is the left side. So this is the anodic half, this is the cathodic half. We are joining them. Okay, so we'll get the full cell. Okay, now this anodic half and this cathodic half has to be same for it to be a concentration cell. That means if this is say a copper dipped in a copper sulfate solution, this also has to be a copper dipped into a copper sulfate solution. So such cells are known as concentration cells. Okay, now if both the half cells are same, how does the electric current flow? Okay, so we say that the flow of the current is due to the difference in their concentration. Okay, one of the solution would be dilute and one of the solution would be concentrated. But if both the solutions are equally concentrated or they have equal molarity, then we'll say that EMF of such cell is 0. Okay, so for a concentration cell to work, the concentration or the activity of the species should be different in both the half cells. Then only a concentration cell will work. So concentration cell is basically two cells that are same are combined together to form a complete cell. Okay, the only difference would be the concentration of the electrolyte or the activity of the electrode. Okay, so let us look at the definition. So this says that a concentration cell is an electrolytic cell that is composed of two same half cells. Okay, so I have already told you we have to take two same half cells with the same electrodes of different activity or different concentration of the ion. Okay, so this you need to remember. So concentration cell is basically a cell that is made up of two same half cells of same electrode, but those electrode can be of different activity or the ion in the solution can have different concentration. So such cells are known as concentration cell. Okay, I will take an example to make you understand this also. So a concentrated cell acts to dilute the more concentrated solution, okay, and concentrate the more dilute solution, creating a voltage as the cell reaches an equilibrium. So I have already told you, because we are having two half cells are same, because their concentrations are different. Because of this difference in concentration, they will have different EMF, due to which there would be a potential difference that would be developed, due to which the electric current would flow. Okay, so you can see that this is written. So concentration cell acts to dilute the more concentrated solution and concentrate the more dilute solution, creating a potential difference or a voltage before it reaches equilibrium. Okay, This is achieved by transferring the electrons from the cell with the lower concentration to the cell with the higher concentration. Okay, so I hope this basic definition is clear. So for understanding of these two paragraphs, let us take an example to understand this. Okay, so we say that there are two types of, okay, so basically there are two types of concentration cell. One is electrolytic concentration cell and the other is electrode concentration cell. Okay, so I will just explain the two types of concentration cell. So in the electrolytic concentration cell, we say that the two half cells are similar. The only difference is the concentration of the electrolyte in the solution. Similarly, for the electrode concentration cell, we say that both the half cells are same. The difference between them is the activity of the electrode. Okay, so let us take an example so that we understand this. Okay, so this is a very common example of a electrolytic concentration cell. Okay, so you can see that this is your anodic half. Okay, so this is your anode. LHS is always your anode. Right hand side is always your cathode. Okay, so you can see that there is a hydrogen, okay, and there is a H plus ion in the solution and it is bubbled through the platinum. Similarly, in the cathode there is a hydrogen, okay, bubbled into the solution of H plus ion through platinum. So both the half cells, you can clearly see that both the half cells is of the same nature, okay, is exactly the same. So you can see that there is a hydrogen electrode in the anode and a hydrogen electrode at the cathode. Okay, so let us say that the partial pressure of hydrogen gas in both the half cells is 1 atm. Okay, and say the concentration of H plus in this solution is C1 and in this solution it is C2. Okay, so first let us write the equation. I have already told you there is a simple algorithm. You have to always write the anodic reaction, cathodic reaction, full reaction. Okay, so let us look at the anode first. Okay, so if I talk about anode, we know that at anode oxidation takes place. Okay, so H2 gas whose pressure was 1 atm would be undergoing oxidation and would be changing into H plus ion. Okay, so we will get this. Now we know that E naught of this is 0 because this is the hydrogen ion electrode. If we look at the cathode, okay, so we know that in cathode there is always a reduction that is happening. So this hydrogen ion will take up 2 electron and will change into H2 gas. Okay, so this EMF is also 0, so the reduction potential is 0 and the oxidation potential is also 0. Okay, so the concentration of H plus in the anode was C1, so this concentration is C1. H plus in the cathode has a concentration of C2 and the partial pressure of hydrogen is still 1 atm. Okay, now let us add the two reactions to get the overall reaction that is happening in this concentration cell. So when we add these two, okay, so when we add these two, you can clearly see that the electron would get cancelled out. Both the hydrogen gas had the same activity or the same partial pressure, so they will also get cancelled out. So we will be left with 2H plus with concentration C2 changing into 2H plus with concentration C1. Okay. Now the overall E naught cell, okay, so the overall E naught cell would be reduction potential of cathode plus oxidation potential of anode, or reduction potential of cathode minus reduction potential of anode, both is 0, so E naught cell would be 0. Okay, because in a concentration cell both cathode and anode are of the same material, so E naught cell for any concentration cell would always be 0. Okay, this is very logical also, because a species is getting oxidized in the anodic half, so it will have a oxidation potential, and the same species getting reduced, okay, in the cathodic half, so that reduction potential would be negative of the oxidation potential. So when you calculate the overall EMF at standard condition, it will always be 0. So we'll say that the concentration cells always have E naught cell as 0. Okay, hope this is clear to you. Now we'll write the Nernst equation. So we'll say that E cell is equal to E naught cell, which is 0, minus 0.0591 upon N, and you can see that was 2. Okay, so while balancing there were 2 electrons, into log of concentration of H plus raised to power 2. Now this H plus, you can see that this H plus is coming from, okay, the anode. So H plus coming from anode divided by H plus square coming from cathode. Okay, I hope this is clear to you. So just you can take this factor square outside. So this will become minus 0.059 upon 2 into 2 log of H plus anode, okay, divided by log of H plus cathode. Okay, so just remember this formula. Now I am just going to use this formula again. Okay, so this will come out to be E cell will become equal to, so for this cell E cell is equal to minus 0.059 into log of H plus of cathode was C1 and H plus of anode was C2. Okay, hope this is clear to you now. Okay, so for this cell to be spontaneous, we know that a cell will only be spontaneous when its E cell is positive. Okay, so for E cell to be positive, so that delta G is negative and the cell is spontaneous, we know that C1 should be less than C2, so that this log term would be negative. Sorry, C1 should be greater than C2, so that this log term would be positive, and when this gets multiplied with a negative sign, it will become negative. So for this cell to be spontaneous, C1 should be greater than C2. Okay, hope this is clear to you. So for this cell to be spontaneous, C1 has to be greater than C2. Okay, so this is basically your electrolytic concentration cell. So in electrolytic concentration cell, we are saying that both the cathodic half and the anodic half are same. The only difference is the difference in the concentration of the electrolyte. Even the electrode, okay, that was hydrogen gas, okay, bubbled on the platinum sulfate, on the platinum sulfur, was having a pressure of 1 atm on both the sides. Okay, so this is the basic example of electrolytic concentration cell. Okay, so a direct question can come on this. Okay, when will this cell be spontaneous? When the concentration of H plus ion in the anode is more than that in the cathode. Okay, so you have to just look at the standard process. So at anode, oxidation is taking place. So H2 is getting oxidized. At cathode, H plus is getting reduced. So overall, this is the reaction which is happening. E naught cell will always be 0. For a concentration cell, E naught cell has to be 0 because both the species are same in the cathodic half and the anodic half. Okay, so this is the final reaction. So we will write the Nernst equation for this final overall equation. So this will be 0 minus 0.059 into log of H plus raised to power 2. This H plus is coming from the anode. Okay, C1 is coming from the anode, divided by H plus raised to power 2. This is coming from cathode. So this is basically H plus anode upon H plus cathode whole square. So we will take this 2 outside, so that will get cancelled out. So this will be minus 0.059 into log of H plus of anode upon H plus of cathode. Okay, so H plus of anode is C1, okay, and H plus of cathode is C2. Okay, we know that the concentration of H plus in the anode was C1 and that in cathode was C2. So if this cell has to be spontaneous, its E cell has to be positive, so that its delta G is negative, because delta G is minus N into F into E cell. Okay, so for that, this quantity has to be greater than 0. Okay, then only E cell will be negative. Sorry, then only, oh sorry, I am again committing a mistake. Now for delta G to be negative, E cell has to be positive, right? So E cell will be positive only when, okay, this C1 is less than C2, okay, because when C1 is less than C2, we will say that, okay, when C1 is less than C2, we will say that this term is negative. Okay, when C1 is less than C2, so this one will be less than 1. So this will come out to be negative and this will get multiplied with a negative sign. So we will get E cell as positive. When E cell is positive, we know that delta G is minus N into F into E cell. Okay. So when E cell is positive, delta G would be negative and this cell would become spontaneous. So this cell is spontaneous only when C1 is less than C2. Okay. That is the concentration of the electrolyte, that is H plus ion in the anode, should be less than that of the cathode. Okay. Hope this is clear to you. Okay, you have to have a very close look, because these are the common mistake that every one of us make. Okay, because I have written delta E cell over here. Okay, and I was talking about delta G as negative. I didn't see that this is E cell, so I just wanted this term to be negative, but this has to be positive for delta G to become negative. So these are the very small mistakes, very silly mistakes that each one of us makes. So just try to avoid these mistakes. Okay. So I hope this is clear to you. So just look at this expression. So we derived E cell as minus 0.059 into log of H plus anode upon H plus cathode. Okay. So I am just going to write that equation again and elaborate on a very important property. So I wrote E cell as minus 0.059 into log of H plus, that is coming from anode, divided by H plus coming from cathode. So I can write this as log of H plus anode minus log of H plus cathode. Okay, so I can write E cell as, this negative I will take inside, so this will become 0.059 minus log of base 10 H plus anode, obviously this is base 10, this will become plus log of H plus cathode. Now we know that pH is minus log of H plus. Okay, so I can write E cell as 0.059 into pH of anode. Okay, so I can write this as pH of anode. pH is minus log of H plus, so this is concentration of H plus in the anodic half. So this represents the pH at anode minus pH of cathode. Okay, because log of H plus would be minus of pH. So this is a very important formula. So whenever we are having a concentration cell of hydrogen ion, okay, that is both the cathodic and the anodic half is hydrogen ion electrode, then we can directly say that EMF of that cell is always 0.059 into pH of anode minus pH of cathode. So this is a standard equation. If you remember this will be very helpful, so you don't have to go through this task and find it over and over again. Okay. Now E naught cell of any concentration cell we know is always 0. Okay, hope this is clear to you. So this was your basic electrolytic concentration cell. Okay, have a snapshot of this. This is a very important formula. Like most of the questions that come in JEE Advanced is related to this formula. Okay. The next comes is the electrode concentration cell. Okay. Now suppose we say that the concentration of H plus ion in the solution is say 0.1 molar. Okay, and this is also 0.1 molar. Okay, so basically their concentration is same. Okay, so in the electrolytic concentration cell we are saying that the activity of the electrode would be same, but the concentration of the electrolyte would be different. In the electrode concentration cell we will say that the concentration of the electrolyte in both the half cell is same, but the activity of the electrode would be different. So say hydrogen was having a pressure of P2 atm over here, and hydrogen was bubbled inside with a pressure of P1 atm. Okay, so we can see that the concentration of the electrolytes is same, but the activity of the electrode or the gas is different. Okay, so again what we will do, we will same write the standard equations. So we know that at anode there would be a oxidation. So hydrogen gas would be changing into 2H plus, okay, plus 2 electron. Okay, so this hydrogen gas was at a pressure of P1, okay, and this H plus ion had a concentration of 0.1 molar. So because oxidation is happening, so I can write oxidation potential. I can also write as reduction potential, so there is no issue. There should be no confusion on this. Okay, in the cathodic half we know that a reduction is happening. So the H plus ion in the solution, okay, will take up 2 electron and change into hydrogen gas. Okay, So the concentration of H plus ion in the cathodic half was 0.1 molar only, and the partial pressure of hydrogen was P2. Okay, so the reduction potential of this would be 0. Okay, so when you add them, we'll get the overall. Okay, we'll get the overall reaction that is happening in this cell. So you can see that these two electrons will get cancelled out. Okay, even the H plus, because of the same concentration, they will also get cancelled out. So we'll be left with only hydrogen gas, which is at a pressure of P1. Okay, it is changing into hydrogen gas at a pressure P2. Okay, now you can see that there is a pressure gradient. The pressure in both the half are different, due to which their individual E would be different. Okay, reduction potential of individual half cell would be different. So that's why there is a potential difference generated, due to which there would be a flow of current and the cell would start producing current. Okay, so let us write the Nernst equation. So the Nernst equation of this would be E naught cell again would be 0. Okay, so E cell would be E naught is 0 minus 0.059 upon n we know is 2 over here. Okay, log of partial pressure of hydrogen. Now this hydrogen is coming from cathode divided by partial pressure of hydrogen at anode. Okay, now E cell, we can say that this is minus 0.059 upon 2 into log of partial pressure of hydrogen at cathode divided by partial pressure of hydrogen at anode. Okay, now for this cell to be spontaneous, for this cell to produce current, we know that its delta G should be negative. Okay, delta G is minus N into F into E cell. So delta G would be negative only when E cell is positive. So this is the criteria for spontaneity of electrochemical cell. So for E cell to be positive, we know that this term has to be negative because there is already a negative sign outside. Okay, so we'll say that for this term to be negative, this has to be less than 1. So pressure of hydrogen at cathode, okay, which is, I think we took it as P2 and this is as P1 na? So we can write this as P2 and this as P1. So we'll say that the partial pressure of hydrogen at cathode should be less than partial pressure of hydrogen at anode. Okay, so this is not pH, this is partial pressure of hydrogen. Okay, so we'll say that P2 should be less than P1. Okay, so when P2 is less than P1, so P2 was basically the partial pressure of hydrogen at cathode, P1 was the partial pressure of hydrogen at anode. So P2 by P1, if it is less than 1, so log of that would be negative, and negative would get, okay, will give us the positive. Okay, so E cell would be positive and delta G would become negative. So this cell would be spontaneous. So you can get a direct question on this. Okay, so we can represent this cell as, okay, hydrogen. So if we start from the anodic half, okay, so I've already told you when you want to enter into the anode, we'll enter through the electrode, we'll encounter the gas and then we'll get H plus ion. Okay, then we are having a salt bridge. When we enter into this, we'll get a H plus ion, okay, that is changing into hydrogen gas and then platinum. Okay, so you can see that, you can easily make out that this is a concentration cell. Okay, the anodic half and the cathodic half are same. Now the this partial pressure was P1, its partial pressure is P2, its concentration is 0.1, its concentration is 0.1. Okay, hope this is clear to you. Okay, so this is how you do it for electrode concentration cell. Okay, now if we wanted to write the cell representation of the electrolytic concentration cell. Okay, so again we'll start with anode. So we'll write platinum. Okay, so we'll first encounter platinum, then hydrogen gas, which is changing into H plus. Then we'll encounter a salt bridge. Then we are entering into the solution. Okay, then we'll again encounter the hydrogen gas, and then through platinum or the electrode will come outside. Okay, so this is the representation. Okay, you can see that both the half cells are same. Okay, only difference is the concentration. So H plus was here having a concentration of C1, H plus is here having a concentration of C2. Okay, the partial pressure of hydrogen here was 1 atm and here it is also 1 atm. So this is an example of a electrolytic concentration cell because the concentration of the electrolyte was different. Okay, I hope this is clear to you. Okay, so this was electrode concentration cell. Now let us take a case in which, say, this is having a pressure of P1, this is having a pressure of P2, this is having a concentration of C1 and this is having a concentration of C2. That is, the concentration of electrolyte as well as the partial pressure of hydrogens are different. Okay, so again we have to write the Nernst equation. Okay, so first we will write the anodic half cell. So we know that at anode oxidation takes place. So H2 gas would get oxidized into 2H plus 2 electron. Okay, so this partial pressure is P2 and its concentration is C2. Okay, similarly at cathode we will write this as H plus is taking up 2 electron because at cathode we know that reduction is taking place. So H plus will take up 2 electron and change into hydrogen gas. So the concentration of H plus is C1 over here and the partial pressure of hydrogen is P1 over here. Okay, so if you add both the reactions, so these electrons will get cancelled out. So the final equation will become H2 gas plus 2H plus aqueous is changing into 2H plus aqueous plus hydrogen gas. Okay, so this hydrogen gas is having a pressure of P2, this H plus is having a concentration of C1, okay, this H plus is having a concentration of C2 and this hydrogen is having a partial pressure of P1. Okay, so this is the final equation. So we know that again the oxidation potential of this is 0, okay, the reduction potential of this is 0, so the overall E naught cell would be 0. Okay, so this might be very clear to you, okay, because if one species is getting is going oxidation and the cation of it is undergoing reduction, so E naught cell has to be 0. Okay, suppose it was a silver over here. Okay, so silver is changing into Ag plus plus electron. Okay, silver changing into metal ion electrode. So Ag changing into Ag plus electron, so it would have some oxidation potential. Okay, and Ag plus taking up electron changing into Ag would have a reduction potential which is negative of the oxidation potential of silver changing into Ag plus. So when you write the overall reaction, E naught cell will always come out to be 0. So for a concentration cell, E naught cell has to be 0. So we'll just write the equation. So E cell we know is E naught cell is 0 minus 0.059 upon 2 N is 2 again, okay, log of H plus concentration raised to power 2, okay, so this will be C2 raised to power 2, okay, into partial pressure of hydrogen which is P1 divided by, okay, partial pressure of hydrogen which is P2 into H plus raised to power 2 which is C1 square. Okay, so this way you will be able to calculate the EMF of this cell. So P1, P2, C1, C2 would be given to you. You can calculate the E cell. Okay, I hope this is clear to you. So this is the case when all the concentration and the activity of the electrode is different. Okay, so a very important formula that we have derived for the electrolytic concentration cell is E cell was always equal to 0.059 into pH of anode minus pH of cathode. Okay, I hope you remember this formula now. Okay, so I hope this is clear to you. So this is all about concentration cell. So now let us try to solve some questions on concentration cell. Okay, so we have to find the EMF of this cell. So obviously I can see that there is a hydrogen ion electrode in the anode and hydrogen gas at the cathode. So both the electrodes are same. So we know that it is a concentration cell for sure. So E naught cell would be 0, but we have to find the EMF. Okay, so EMF I have already told you would be 0.059 into pH of anode minus pH of cathode. Okay, because you can see that this is a electrolytic concentration cell because the pressure of the partial pressure of the hydrogen gas is same in both the cases. So obviously the concentration different concentration is different for the electrolyte. So this is the electrolytic concentration cell. So for pH of anode, okay, we know that the concentration of H plus is 10 raised to minus 6. So this will be minus log of base 10, 10 raised to minus 6. So this minus 6 will come out and it will become plus 6. So pH at anode is plus 6. If we consider the pH at cathode, okay, so this would be again minus log of base 10. Okay, this is 10 raised to minus 4 because the concentration of H plus at cathode is 10 raised to minus 4. So this minus 4 would come out and this would become plus 4. Okay, so this is the formula. Okay, so pH at anode we know, pH cathode we know. So E would become 0.059 into pH anode, which is 6, minus pH cathode, which is 4. Okay, so this will be 2, so this will be 0.118 volt. Okay, E cell is positive, that means this is a spontaneous cell. So if we need to find the delta G, so delta G would be minus N F into E cell. Okay, N here is 2. Okay, you can clearly see that N here is 2, so delta G would be minus 2 into 96500 coulomb into E cell, which is 0.118 volt. So this would be the answer of delta G. Okay, I hope this is clear to you. So this is basic application of the formula. So what I am doing, I am understanding the theory first, getting into the skin of it, extracting the main concept involved, and then just applying in the questions. Okay, hope this is clear to you. So let us look at this question. So first just look at the half cell. So this is hydrogen, okay, H2SO4, that means hydrogen in a hydrogen ion. Okay, so hydrogen ion electrode is there. So this is basically gas ion electrode. Okay, now look at this. This is KOH 10 raised to minus 3 hydrogen gas at 1 atm and platinum. Okay, so this is also a hydrogen ion electrode. Now in this case we have been given the concentration of OH negative. So we can find out the concentration of H plus. Okay, so this will eventually become H plus H2. So we have to find the concentration of H plus because we know that concentration of OH negative is given to us as 10 raised to minus 3. Now because this is again a electrolytic concentration cell, the activity of the hydrogen gas is same. So we will say that E cell is always 0.059 into pH of anode minus pH of cathode. Okay, so if you look at the anode, now in anode the electrolyte present is H2SO4. Now H2SO4 is a diprotic acid, so 1 mole of H2SO4 will produce 2 moles of H plus ion. So 0.05 molar H2SO4 will produce 0.1 molar H plus ion. So H plus ion in the anode is 0.1 molar. Okay, these are the basic that you have to take care while solving a question. I know mistakes happen, silly mistakes happen, even I do the silly mistakes, but as a human we keep on learning how to avoid those. Okay, so the only thing required is the full concentration. Still it might happen that even after full concentration you are missing out on 1 or 2 things, but don't worry about that, that gets rectified as you proceed. Okay, so with time these kind of problems or these kind of mistakes will get rectified. Okay, so at anode we know that the concentration of H plus is 0.1. Okay, so the pH would be minus log of 10 raised to minus 1 base 10. Okay, so pH at anode I can write as 1. Okay, so the pH at anode is 1. Now let us look at the pH at cathode. Okay, so we know that at cathode we are having OH negative. Okay, KOH is a strong electrolyte, it would dissociate into OH negative and K plus. So the concentration of OH negative over here would be 10 raised to minus 3. Now we know that H plus into OH negative at room temperature is always equal to 10 raised to minus 14. Okay, so I can write H plus as 10 raised to minus 14 divided by concentration of OH negative. Now the concentration of OH negative is 10 raised to minus 3. So this would become 10 raised to minus 14 divided by 10 raised to minus 3. So H plus concentration would become 10 raised to minus 11. Okay, hope this is clear to you. So we'll say that the pH at cathode is 11. Okay, now this is very obvious because this was a basic. Okay, the cathodic half was basic because there was KOH, so it is basic, so its pH would be 11. Okay, so we'll just use this in the formula. So E cell would be 0.059 into pH anode, which is 1, and pH cathode, which is 11. So this will be minus 10. So this would be minus 0.059. Okay, hope this is clear to you. So these are the basic questions that are formed on the concentration cell. Okay. So let's look at our last question before we end the session for today. Okay, so just have a feel of this question now. So this says that we are having a hydrogen gas and we are having acetic acid, okay, as the electrolyte. So this is also H2, and acetic acid will produce H plus ion. So this is also acid gas in its aqueous solution containing the H plus ion. So this is basically hydrogen ion electrode, and in the and if you look at the cathodic part, so this is basically cesium hydroxide. This is a base. So from base you can calculate the concentration of H plus, because we know the concentration of OH negative. So that is again a gas ion electrode. Okay. So for acetic acid, now if you look at the question that was before, the electrolytes that were taken were strong electrolyte, but acetic acid is a weak electrolyte. Okay. So we know that acetic acid would not dissociate completely. Okay. So if the concentration of acetic acid is 10⁻²⁻² molar, the H plus concentration won't be 10⁻²⁻² molar, because it is a weak electrolyte. So this would break into acetate ion and H plus ion. Okay. So say at time t equals to 0, the concentration was C. If alpha is the degree of dissociation of acetic acid, we know that after time t, when equilibrium is established, C alpha of acetic acid would dissociate. Okay. So C alpha is dissociating, so left over would be C minus C alpha. So 1 mole of acetic acid is producing 1 mole of acetate ion. So C alpha amount would produce C alpha of acetate ion. 1 mole of acetic acid is producing 1 mole of H plus. So C alpha that dissociate would be producing H plus ion as C alpha. So the concentration of H plus is C alpha. Okay. Now we also know that the acids have a acid dissociation constant Ka. So this will be equal to concentration of acetate ion into H plus ion divided by acetic acid. So we can write this as C alpha into C alpha upon C1 minus alpha. So if you cancel out C, so we'll be left with C alpha square upon 1 minus alpha. Okay. So because the acid is weak, so we'll say that 1 minus alpha is approximately equal to 1. Okay, because weak acid dissociate to a less extent, so alpha would be very much less than 1. Okay. So the expression would become K is equals to C alpha square. So alpha I can write it as root of K upon C. Now H plus I know is C into alpha. Okay. So I will write H plus as root of K into C. Okay. Hope this is clear to you. Now if I want to find the pH of this, okay, so I will just take log on both the sides. So log of H plus would become log of Ka into C raised to power half. So if I take a minus sign, so this will become minus log of H plus. Okay, half will come outside, so this will become minus log of Ka minus log C. Okay, so this is just the basic mathematics that I am doing. Excuse me. So this is half. Okay, we'll take it just outside because this is a log. So this is log of x into y, which is log of x plus log y. Now we have taken minus sign on both the side. So minus log of H plus will be equal to minus log of K minus log of C into half. So this is basically your pH. So I will write this as half minus log of K. I can write that as pKa minus log C. Excuse me. So this is the pH. Okay, so this is the pH of the weak acid, acetic acid. Okay, so this is the pH of a weak acid, acetic acid. Okay, so I hope these steps are clear, generally taken from ionic equilibrium. So first we are getting the value of Ka, which is C alpha square. Okay, for a weak electrolyte. H plus we know was C alpha. So H plus is root of K into C. So we are just taking the log. So log of H plus would be log of K into C. So this half will come out. Then we are taking minus on both the sides. So this will become minus log of H plus, half we have taken outside, minus log of K minus log of C, minus log of K is pKa and minus log of C. So this is the formula. Okay. So because this is the concentration cell, so we know that pH is 0.059 pH of anode minus pH of cathode. Okay. So what I can do over here is, we know that the concentration of OH negative in the cathode is 10 raised to minus 11. Okay, so we know that H plus into OH negative at room temperature is always 10 raised to minus 14. Okay, so when you put OH negative as 10 raised to minus 3 over there, so we'll get H plus as 10 raised to minus 11. Okay, so 10 raised to minus 11 means pH would be 11. Okay, so the pH of cathode is 11. Now we have to find the pH of the anode. Now anode is having a weak acid. Okay, so that would be pH of anode would be half into pK minus log C. Okay, so this is half. pK of acid was given to us as 4.74 minus log of C. C was given as 10 raised to minus 2. So we'll just take 10 raised to minus 2 over here. So this will come out and this will be added in this. Okay, so this will be half into 4.74 plus 2 minus 11 into whole into 0.059. Okay, so you can calculate this and you will get the pH of this, okay, particular half cell, this particular concentration cell. Now question can come also like this. You will be given this pH value, you need to find out this value of pKa. So that again becomes the question of integer type. Okay, so everything will be given to you, just you need to find this pKa value. Okay, so I hope the steps are clear to you. I hope you understood how we are getting the pH of a weak acid as acetic acid. Okay, so just we are using that. So we know that for electrolytic concentration cell, pH has to be pH anode minus pH cathode into 0.059. Okay, so we are finding the pH anode, we know the value of pK, we know the value of C. Okay, so we will calculate the pH at anode, we will calculate the pH at cathode, we will just subtract them and multiply with 0.059. So this is how you solve such kind of question. You can see that there is a good application of ionic equilibrium in these questions. Okay, I hope you have understood this question. So this is a very important lecture. So these questions are very important for JEE Mains as well as JEE Advanced, especially for the JEE Advanced as well as Olympiads. So if you are facing any problem, just revisit the ionic equilibrium lecture, because the basics of different kind of concept of ionic equilibrium has been covered over there. Okay, so I hope you enjoyed the lecture today. So this is Animesh signing off for now. We'll catch tomorrow for some good high level problem solving as well as thermodynamic parameters of galvanic cell. Thank you everyone.